All right, so here's day 2 of Factor and FOIL. And I know I might be going a little bit fast. I want to keep these videos short, and you can always pause, you can always rewind. Um, so let's continue a little bit from yesterday. I want to let you know that if you see something squared, and I know I kind of wrote on top of it, get out of the way, something squared, what I don't want you to do is, I'm going to make that 4x or 16x squared and then 1, because you're missing a whole bunch. This just means they are two things side by side. If I had x squared, I have x times x. So all of this squared means all of this times all of this. Make sure you FOIL correctly. Combine your like terms, just like that. I will also say, when you see this, and you only get two terms, a 16x and a 1, you should remember there's something in the middle, and it's going to be the same thing twice. There's a whole reason why there's a 2 kind of in this formula. It's the same thing when you have an extra variable or whatever, y squared, and y squared is just y to the 4th. And I have some y squares in the middle because of the outside and inside, and then my last terms make positive 4. Again, I just don't want you to distribute or whatever. Now this one's already set up side by side. This is a special case. I can get x squared and x squared, and then I'll get minus 3x squared y plus 3x squared y, and then minus 9y squared when I FOIL. Problem is these cancel. Okay, so just like last video, if I have 0x squared y, I'm not going to write it. If those cancel out, I'll need the x to the 4th, I'll need the minus 9y squared, and then I'll be done. So just be careful on some of these special cases that you know this is not just distributing, and that if something cancels out, it's fine. Just make sure you don't write it down here. Then we talked prime factorization, and I talked about the factor tree and how the factor tree is dumb. But prime factorization, first of all, you need to know what a prime number is. It's a number that can only be divided by itself and 1. 1 is not technically a prime number. There is a great mathematical debate about it, but basically because it does not have two factors, two separate different factors, 1 does not count. So our first prime number is here at 2. 1 times 2. There's no other way to multiply to 2. Then we go to 3. The only way to multiply to 3 is 1 times 3. Prime number. Then we go to 4. 1 times 4 or 2 times 2. As soon as you get that second set of numbers, that is no longer a prime number. It's called a composite number. 5 is 1 times 5. 6 doesn't work because it would be 3 times 2. 8 doesn't work because it's 4 times 2. 10 doesn't work because it's 5 times 2. 12 doesn't work because it's 6 times 2. That's why we stop writing even numbers, because every single one of them past this one is the only even prime number. Past them, none of them will ever be prime. 9 is an odd number that's not prime because 1 times 9 and 3 times 3. 11's prime, 13's prime, 15 is not because 3 times 5. I've already broken it down. 17, 19, 21 is 3 times 7, and prime numbers go on forever. What we're going to do is we're going to use those prime numbers in order, and we're just going to divide. We're going to divide until we can't divide anymore. So if I want to prime factor out 54, I think to myself back here, what's the first number I should probably use? Let's start with 2. Especially if it's an even number, which it is. So I'm going to divide by 2, and I'm going to get 27. Now, can I divide by 2 anymore? No. So then I go, what's the next prime number I can use? Let's try 3. 27 divides by 3 and gets 9. 9 divides by 3. I don't need to go back to 2 because if this doesn't divide by 2, this is not going to divide by 2. Divide by 3, and I get 3. Once this is another prime number, and it can't be broken down anymore, that's where we stop. All the stuff that got boxed off here, we don't need those numbers anymore. It's just these numbers on the outside. Those become my prime factorization. We divided to separate them, so we would multiply them to put them back together. Prime factorization. When we do it for 2 of them, move these out of the way real quick. 56 divided by 2 is 28. Divide by 2 is 14. Divide by 2 is 7. 7 is a prime number. 2, 2, 2, and 7 multiply together get 56. 104 divides by 2, divides by 2, divides by 2, and I get 13. 13 is another one of our prime numbers. To find the greatest common factor, we're looking for what do they have in common. What kind of pairs can I make? Well, I have, and let me do it this way. I have a pair of 2s. I'm going to mark them as a single 2 down here. This represents one of your pairs. I have another pair of 2s down here. I have another pair of 2s down here. 7 and 13 don't match. I don't have any other numbers. So I piece all these back together, multiply them, and I get 8. 8 is the greatest common factor. It is the biggest number that can divide evenly into both of these. And we found it just by breaking them apart and figuring out what kind of matches we can make. Which is what they did, but they used the factor tree, and I really don't like the factor tree because, first of all, it could get a little disorganized. They went and did 7 and 8, and did 4 and 26, and broke these down. But well, what happens if I need to break this down and then break this down, and then I got this number right here that's it's no good. So I like our method a little bit better. Excuse me. Here's a couple more examples. Just let you write them down. But again, you're looking for pairs. Pair of 2s, pair of 2s, pair of 2s, pair of 2s, pair of 2s. No pair after that. Now this one, let me grab my highlighter again. I have a pair of 2s, and I have a pair of 2s. The problem is, those are not in common over here. Greatest common factor means they got to have the same thing in common. So those 2s just get left over, kind of like the 5 and the 3s down here. But I do have a pair of 3s and another pair of 3s. So I have a 3 that's left over also, which is fine. It's not quite what I'm looking for. So the stuff that I did find pairs of, multiplying back together, 18 is the largest number that goes into both of these. Now, 3 numbers that have a greatest common factor of 50. Sorry, it's crossed out. 50 is 2 times 5 times 5, which is 25 times 2, or 10 times 5, however you want to look at it. Really, take those and then multiply by one more prime number, whether it's 1, 2, or 3, or 5, or whatever. What I don't want you to do is multiply by numbers that aren't prime, because you could get in trouble. This would be 2, this is 4, and this is 6. 50 can go into all of these, but it's no longer the greatest number that can go into all of them. That now belongs to 100. So that's why it is no longer greatest common factor of 50. So just be careful. Florist is making identical bouquets using 35 white, 45 red, 105 pink. We need the greatest number of bouquets if no roses are left over, because you could go, oh, well, we'll just make 35 bouquets with, you know, one of each, and that's a really sad bouquet. We don't want to be wasteful either, so no roses left over. Really all you can do is find your greatest common factor. I got all these factored out, and 5 was the only thing that was in common with all 3 of them. Okay, just because I have a 7 there and a 7 there, for it to be a common factor, it has to show up in all 3. Same thing with a 3 there and a 3 there. They have to show up in all 3. 5's the only one that does. So we're going to make 5 bouquets. Well, how do I know how many flowers of each? Well, guess what? All these leftovers are going to tell us. We're going to have 7 white. We divided these, so 3 times 3 gets put back together to be 9. 9 red. 3 times 7 is 21 pink. And that's the end of that one. And again, I'm sorry if I'm going real fast. I'm trying to keep these short. This is already a 10-minute video, but it'll keep you caught up.